Okay, I'll begin the lecture. In the last lecture, we remember we stopped at this part, rejection sampling. So once again, I mentioned that we'd like to generate samples for the problem I mentioned once again. We'd like to generate samples for a distribution Px. Usually, this is the posterior distribution in our study. And we cannot generate the samples directly for this. So instead, we introduce an arbitrary proposal. We call it a proposal distribution, Qx. This has the sampling capability, like a normal distribution, whatever distribution, from standard PDF. And introduce another one called M, a constant. Yes?
So how do you come up with this Q of x and this M?
You mean the how do you, in what way you introduce the proposal distribution Q?
Yeah. Like you have to assume a Q of x. How do you assume a good Q of x?
It's a difficult question. How do we employ Qx, choose Qx among the many given known distributions? The answer that I can say is the once we have the shape of the original Px, whatever it is, we can draw some shape of this, and the criteria or guideline is let another distribution cover this original one like this, the whole PDF value.
Right, but we cannot, we don't know the shape of P of x, right?
Px. At least we can draw the shape of this because we have the expression at hand. The problem is we don't sample. We can draw, we can calculate the p-values at any x. So we shouldn't be confused. We can calculate p, but we cannot draw samples. So another question.
Yeah, I was curious, maybe I'm confused here, but how is it that the other curve fully covers the other one, given that they're both probability density functions?
Given that they both probability density function, P and Q, I will explain how we can cover the whole of this Px using Qx. I will explain this in the MATLAB implementation. Very easy thing. And that's why I am introducing a constant M. So you will see what it means. So the process was because once we have another proposal distribution Q, we can sample. We can generate samples satisfying Q, like 1,000 numbers. You imagine for Q, like normal distribution, we can easily make samples following normal distribution. So right now we have 1,000 samples of normal distribution. And they can be placed along this x-axis. We have 1,000 number of x here. And at a point, at an individual sample value, we call it as the realized value. At an individual value of the sample like this, we calculate this, Px and MQx. Remember that M should be introduced such that the MQ should cover the whole Px height. I will explain using the example. So we have the ratio the value of this ratio, and it varies within 1 and 0. And if this value is high, it means the probability to get this is high, because along this line, this represents the relative height of px conditional on mq. And if this height is close to 1, we have a strong likelihood, we have a high probability to take this value as the sample. In other case, if this value is quite low, like this region, we have much less probability to take this sample of the px. So in this way, we repeat all the samples and make decision whether to take this as a samples or not. If it's not, they are rejected. So only a part of the total numbers may be accepted as the samples for px. Once again, I use this distribution for the problem. By the request of a student, I made it the line width increased, so for more visibility. Previously, it was a very thin line, and so this is the function. This is the distribution that we would like to make samples. We don't know how to make samples directly from this. So we introduce another probability density function that we can make easily. Is from this time. So I hope you guys will have this codes or documents at your hand, in case you don't see clearly here. So this is the line. I introduce another probability density function that we sample easily, which is norm PDF. We can see what it looked like in this original PX. The normal distribution that we introduced with the mean at 5, standard deviation with 10 will look like this. And this low height PDF doesn't cover PX at all. So we have to introduce a constant such that it covers the maximum height. That's very easy. At every point of x, we compute the ratio and make m, the constant, greater than the maximum of p by 1.1 times. And we will see the results again here. This. So this is the results after multiplying a constant, so that should cover the original PX. And the rest is, I use 10,000 numbers to generate samples satisfying this normal distribution, and calculate the ratio. It's very easy in the MATLAB implementation using the convenient command. So P divided by Q, M. And I introduce another random uniformly distributed values. Here it's capital U. And compare U and R. If U is less than R, then we accept, because R is high enough to be samples of px. So only a part of the entire samples are taken from here, and the number of that is n1. So after going through this line, what we get is this number. I told you the original number of samples, 10,000. And only this number are taken as the samples for px. The others rejected. And using this number, we can draw histogram like this. And because we can draw px, although we don't sample, we can still draw the function values and draw the shape. So we can draw that on top of this and get this result. So now we got the result. Now we got samples for px with this number.
The quality of this sample will be highly affected by the M you are using, right? If you use very big M.
So if time is allowed, I was going to let you practice. Try different constant m. At this time, I showed you 1.1 times, but we can also try another value and look at what happens.
So 1.1 is good value.
Yeah, that value I chose arbitrarily.
Okay.
But it should be greater than 1, at least. Yes.
So would it be correct if I say the acceptance rate of the sampling is just determined by the ratio of the areas of the distributions?
Yes.
So for example, the example in the slide, I think the acceptance ratio is about 50% according to the ratio.
Yes.
Of the
Out of 10,000, we had the about 20,000.
So if we increase like the R value, you use 1.1
Yes.
in the matter of example.
Yes.
If we increase or if we take a higher value, for example, R is 2, so I guess rejection rate would increase.
Right.
We have like a
So with this example I showed you, it was like 15%, and 85% were rejected. But if we increase this level, M, we get further the more rejection rate.
Right, that we have to sample twice in this case. We have to sample once to get the Q of X and M, and then sample again to actually sample for P of X.
We need sampling only once from QX. And the next step is just manipulating with those samples. I mean, accepting or rejecting, using those samples. Sorry, I did not repeat your question. For the students remotely learning this class. Did you get it? Okay. I did not apply this method to my research. I just went through this process to get some understanding of this method. So if there may be further more higher level questions for this method, I cannot answer to that. So I will move to the next method. By the way, before going to that, I have a remark. And this is the remark in any articles addressing this method. It's not always possible to bound with reasonable amount. This example, this problem is very easy, and we can handle easily the case that we have to know, like proportional constant m and the range of the px, things like that. But in reality, it is not that easy. So for that reason, it is not always possible to find out the qx, and find out m sufficient to bound the px in the entire region. So that is kind of a drawback of this method. Next is the importance sampling. In this method, we introduce also the same thing, an arbitrary probability distribution, qx, and this has the sampling capability. And we still don't have the sampling directly from px. The purpose is always the same. We don't have the capability for px, so we introduce another one that has the sampling capability, the same thing. But in this case, the q doesn't have to cover the px. So in this case, it doesn't matter. The introduction of this qx in the importance sampling, we can make several calculations. Firstly, the moment or expectation, or calculating probability, or even generating samples. Out of these things that I can do, this is the thing that we really want, because we are interested in how to generate samples out of px. So with this thing, I have to explain primarily. But in order to explain this, in order to understand this, you need to understand before these things first. So the way to calculate expectation of some arbitrary function is defined this way. This is the nothing but the integration of a certain function f times the probability distribution p, and this is the original definition of the expectation or moment of fx. And we transform p into w times q. And obviously, w is the p divided by q. And we get the same thing. And in order to calculate this value, we do this in discrete way. So the discrete version of this will be this one. And here, the thing is, we first generate samples from this one, the proposal distribution Q. So we have the samples, large number of samples following Q, and at each individual sample point, we can calculate fx and wx. W is, the meaning of this is the weight between, or ratio, which is the p divided by q. So by applying this equation, we get the result. And also, during this process, the weight should be normalized based on this equation. I will, yes.
What do you mean by the px is not normalized? I thought px is PDF. It's already normalized.
Px, usually I said that px is the posterior distribution in our study, and it's not normalized. So I will also how to make this using this problem. Previously, I already made samples for px, which was from the rejection sampling, which was the with the 15,000 numbers. We can use those samples to calculate these things: the mean, variance, confidence bounds, or CDF values, whatever. Once we have the samples, we can calculate whatever kind of things. In this case, it was the mean of this distribution was, we found from the samples, 7 point something. Like at this point, it's kind of a center of the area along this line. The mean, another meaning of the mean is like this. So we can calculate the mean, variance, and confidence bounds, whatever, using the generated samples x. And also we can compute the probability less than 5, which is the area along here. Or we can also do another value like probability x less than 15, which will be almost 1. So these values are actually calculated like this. If we want to calculate the mean of that distribution, mean of this distribution, we already calculated it 7 point something. And I will use the importance sampling method for this, assuming we didn't know before. For that purpose, we have to use the expectation equation, because the meaning of mean is this one. So we have to know this is the mean. And in this case, this is the function fx. So once we have generations of qx samples, then we just apply. I showed you in the slide. Here, as a specific example, I am explaining the case that fx is just x. And it is the mean of the probability distribution px. And in order to apply the importance sampling to this case, I just make samples from qx and compute the weight at each generated samples. We can calculate the weight values. And in this case, I showed you fx is nothing but x. So apply into this equation here x and a w from that, and sum it. And this is given in the MATLAB by this line. So with the 10,000 samples, make samples from qx, which is normal distribution, and we compute the weight and normalize it, and the result is by simply x times w and sum it, and with this we get the result. And this is the result by using importance sampling. This is the result that we already obtained from rejection sampling. So in the importance sampling, we didn't even make samples of px. We just stayed at making samples from qx, and we got it. We got the same answer, although a little bit different. So that's how the importance sampling gives us the value. Yeah. I'll move.
So it is always better to use importance sampling rather than rejection sampling because this is more, more general.
I did not see how to make samples from importance sampling yet, and I will explain that. Yeah. So with this, I only showed you how to calculate the mean and variance and things like that, but I did not explain how to make samples. That is our primary interest here. I will skip this one. This another one, and it's not. This is much less important issue here, so I will skip this, and I will move to here. How to generate samples based on importance sampling. The conclusion. By skipping this detailed process, the conclusion is that we have the same situation. We have the same occasion here. We have made samples following QX. This is the condition. And once we have those samples, the PX, this is the one we want. The PX represents weighted samples at each of these drawn points by QX. This is the conclusion. Primarily, in a previous case, if we had the capability to make samples directly, then it represents the same, the samples have the same weights. That's a normal case. But in this case, we don't have the samples for PX. We have only samples for QX. In that case, we can say we have still the samples, but it's from QX. So in this case, we have the weighted samples for PX. And the weights defined by that way. We can calculate because we put some value x, we get the values of p, values of q, and get the values of weights. And once we have that value, we say we have the weighted samples. Yes?
What is delta?
Delta means Dirac delta. Did I say right? Yeah. It is defined only at a certain point. So it's just a mathematical expression. So, and another question, yes. I will explain this through the MATLAB illustration. I do this at once, not step by step. And what we get here is this figure. I am using very small size example, like 10 number of samples. In reality, it's like 10,000, but for the purpose of illustration, I am using only 10 numbers. This is a proposal distribution, normal distribution. This is the one we want. And we can only make samples from this red curve. And let's say we had 10 samples satisfying this one. from norm-rand function. So that may be something like this. Did you get that? So this is the normally distributed samples, 10 numbers. And we calculate weights at each of these sample points. And the height is displayed like this. The reason that we have this height is because of the large value of px. The reason that we have almost zero height is because almost zero px. And the definition of W is P divided by Q. So you will understand why this is very small, this is very high. Okay? In this way, I am saying the points have the weights. And I say this is the weighted distribution. The points are defined on the normally distributed case. I still don't have the samples for px yet, but we can say that the px is the weighted samples in this normally distribution. And soon I will turn this into the samples for px that I call that as the sampling importance resampling. In abbreviation, it is called SIR. And the result is already given here. Because we have this case of weights at each of the points, we can make some kind of an empirical CDF curve here. And this blue curve or line represents the weight distribution along this line. If we have this length at this point, that means we have this weight. If we have this small weight, that means we have this small weight. And generates random number along this line, uniform random number. And the same thing, I explained previously about when I explained the grid method or inverse CDF method, I explained a similar thing. Out of the uniformly generated samples, we find out the corresponding X location. If this is large, we get more samples here. If this is very small, we have very little chance to get samples here. By this way, we generate the samples at this line, at this axis, and this is the answer for px. This is the samples for px. And this is the central concept of the importance sampling. The problem is we have duplicate samples here. 1, 2, 3, 4. All these points goes to a single point. So we have 4 or 5 number of samples at a single point. That is another drawback of the importance sampling, but this is the real case. Many people are using this method when they talk about the importance sampling. So, yeah.
But will this method still be better than rejection sampling?
I would say it's not a matter of which one is better or not. Matter of kind of a preference. In fact, this is really massively used in the prognostics, because I am working on the prognostics in the research area, and there is a method called particle filter, and within that method this is used. So this is the the summary of chapter 10 of Gelman's textbook. Very obvious. The inferences can be much more convenient using the random sampling or simulation. And I have shown you a few methods for this. And once the samples are obtained, it is very easy to make further evaluation. Many things can be done easily. And regarding the normalized and unnormalized case, I already explained as well. In our case, the thing is the distribution is not normalized. It is proportional to a normalizing constant. Still, we can make the samples even in this case. And the last thing, the most important thing, I did not show you the importance of this one, but in reality, this is much more important, much more difficult. And we spend much more time to find out the effective range of the px, things like that. And the first thing we can do is perform or carry out the optimization to find out the mode or the maximum height of the px and find out the upper bound, lower bound. For doing that, we put many efforts. And I didn't show you the case. This is the end of the simulation. And I move to Markov chain Monte Carlo. Have to make it in 10 minutes. If I don't make it, I will reserve these things for the next class. After Professor HAFTKA makes his class next week, and I will take another class from the week next week, and at that time I will continue this. So here are some historical notes. If somebody has time to read this, I strongly recommend. And before getting into the MCMC, we need to have some understanding of the Markov chains. There are good readings, and rest is the MCMC. So I have to explain at first what is Markov chain. And there is a good example found on the internet, which is the weather in the land of Oz. And I did not watch this movie, but I know that this is very famous in United States, not in my country. So I don't know the story. So I don't know why this is very unique, but I will explain. Rain, nice, snow represent RNS. And very strange weather system. If today is nice, tomorrow never nice. Or instead we have a chance to have snow and rain 50-50. If today is rain or snow, we have the 50% chance the same the next day. And if it is changed, we have the half of this change to nice. Based on this, we can construct this matrix. Let's consider one. Today is rain. And what are the probabilities for tomorrow? Rain, nice, sunny. Not sunny, sorry. Snow. I told you, if today is rain, we have a 50% of the same, so we put a 50%. And the rest, if changed, only half of this is changed to nice. So this is the result. Next, today is nice. Tomorrow, nice again, not nice. So we have the 0 probability. And the others, we have a 50% because we have a same chance either of snow or rain. So this is correct. And the rest, the same. So this is the matrix. And the thing is that we can construct the weather results based on this information sequentially. If we have a rain today, we can generate sample for tomorrow, whether it will be nice or snow. And we make the history of weather states in a sequence. And the thing is that the next day state is affected only by the today's states, not by the previous history. Only from today we get the next day's states. This is very important point in the Markov chain. Based on this, let's make answers together. Today, rain. What's the probability of S tomorrow? Today's rain. What's the probability of S tomorrow? This one. And more difficult case. Today's rain still. And what's the probability of S day after tomorrow? It's quite tricky from now. But you can think about that. We don't know the tomorrow, so we have the probability instead for R and S like this. And based on each of these, we can make the probability to get the snow. For example, probability for rain tomorrow is 1/2. And based on this, what is the probability to have snow is this one. In this way, you will soon see the results will be made by operating the matrix operation in this way. And in terms of mathematics, it is written here like this. Once again, I repeat. The next day, tomorrow's probabilities are P11, 12, 13. 11, 12, 13. We have 3 different probabilities for R and S tomorrow. And we move to tomorrow. And let's say we have the rain tomorrow. What is the probability for snow? It is here. Let's say we have the nice day tomorrow. This is here. What is the probability to have snow day after tomorrow? This is here. So in this way, we can make the probability. And mathematically, this represents the first index is the given thing. And the second index is the prediction. So based on what we have, which is 1 means rain, we get the probability for 3. 3 means a snow for day after tomorrow.
So they have a super 2 on P13. The P13 on the left is not the same as the P13 on the right.
Oh, yes.
Should have a super 2.
Right. Superscript should be put here, sorry. And in terms of matrix operation, it is given in this way. In the MATLAB code, this is a simulation, so I have to find out the code for MCMC. I have to pull out the code for MCMC here. Open. I was having difficulty to pull the code up here at the beginning of this lecture, and it's still the same. So I don't know why it is not coming here. I'd like to look at the code. What's wrong with me? Open. Nothing happens. It's trouble. I don't know the reason. I will continue explanation. The thing is that using the same way, we can make answers like that. This, after many days, like 100 days, what are the probabilities of rain, ice, and snow? And the result is by making this operation. So multiply 100 times of the matrix here. And we get the, surprisingly, get the same probability distribution for R and S. No matter what state we start, we get the same distribution. That is the answer. And I was going to show that using the MATLAB code, but it doesn't work. And this is the most important concept used in the Markov chain, Monte Carlo. And I will continue. And sorry for not making the MATLAB code here. Any questions? Anybody that can help me how to make the MATLAB code appear here? I don't know the reason why it's not working. It doesn't come here. Okay. So I will see you a week after next week.